Okay, so we're going to continue our video of what to do once we've completed our funicular polygons. Now I'm going to move from MathChat and I'm going to transfer over to AutoCAD just because it lets us do dimensions. There's no way in MathChat to, for example, find out the length of a line. So, as if by magic, he says, you'll see we've got a similar setup. I've tried to keep the colours the same. So what's different? Well, I've numbered the joints there, there, and there. I've numbered the joints there, 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 and there, and I've put a table up, and we'll be filling this table up as we go along. So, where do we go from here? Well, first thing we need to do is we need to find our reaction forces. So there's reaction force 1, there's reaction force 2, there's reaction force 1, there's reaction force 2. So how do we find our reaction forces? Well, the purple line in both cases gives us the space between our reaction forces. Okay, so in our case it's point A, and I've already labelled that up there, as you can see. So we're going to just drop that. Zoom in a bit, just drop that. He says there. Okay, so that's point A. Okay, and what that means is, well, if we look at our funicular diagram, if we go from C round to A, then that's reaction force 2. So from C to A is reaction force 2. Yeah. Again, we go from D to A, that's reaction force 2. We go from D to A, that's reaction force 2. We go from A to B is reaction force 1. A to B is reaction force 1. So what we need to do then is we just need to measure. So let's put some dimensions on this. So we go from there to the intersection. Okay, and that's 50. Yeah, as we expected, yeah, it's 10, it's symmetrical, so it's going to be 50 either side. This line was 100 long. So let's just get rid of that confusingness. Sorry, I thought I'd got this all set up. So that's 50, and obviously that's going to be, so that's 100 long, so that's 5 newtons, because I'm 1 to 10 scale, or 10 to 1, I always get those two confused. That's 5 newtons and 5 newtons. If we measure that, that's going to be 50 as well. Okay, so we've put some dimensions on it. So let's flip over to here and let's do the same. Let's hit that dimension button. Oopsie daisy. Let's zoom in so we can see what we're doing. We go to the intersection. Okay, so that's 10.3 newtons if we're rounding up, and from there to there is 6.7 newtons if we're rounding up. Okay, so that's our reaction forces. So let's just label those up now. So you can see I've already filled in the table here for that. So what do I need? I just need to copy some text down there. So we've got our 5 newtons there, and we've got our 5 newtons there. And what did we say here? We said that was 10.2. So let's just edit that. 10.2, 10.3. 10.3 newtons and 6.8 newtons. 6.7 newtons. Let's see, we need to get to 17, don't we? So 17 minus 10.3 would be 6.7 newtons. Okay. So obviously we've got a bit of a rounding error there, but we could be more accurate if we wanted, couldn't we? Okay, so we've got our reaction forces. Okay, so I'm just going to fill that in on my table. So AB is 6.7 and is 10.3. Okay, I don't know why it's putting in loads of zeros. There's obviously a setting somewhere. Never mind. Just move that out of the way there. Okay, so we found our reaction forces. And that's the purpose of the funicular diagram, is to find the reaction forces. So now we need to find out the forces in each member of our frame. So here we've got 3 members, here we've got 1, 2, 3, 4, 5, 6, 7. Okay. So how do we do that? Well, let's start off by zooming in on joint 1 in each case. Okay, so in the easy for me to say, in the best traditions of TV, here's one I prepared earlier. So zooming in to joint 1. Okay, so what we're looking at, BDA there, and we're looking at BEA here. So let's just change that to E. Okay, so there we go, we've got that. And we know that that is 6.7. So that's 6.7, and we know that that's 5. There we go. Okay, so what do we do with this? Well, we've zoomed in. We start by drawing what we know. And what we know is that we've got 5 newtons and 6.7 newtons. Okay, so I'm just going to draw a line from there, and I'm going to make that 50. Okay, and I'm just going to copy an arrow. There we go. So that's our first one. I'm just going to draw a line from there. I'm going to make that 67, because that's the scale I'm working to. And again, I'm just going to pop an arrowhead on there like that. Okay, so that's what we know. And we also know that we're starting at A and we're going to point B. Okay, so we're starting at A, and that's a lowercase a for our force diagram. Okay, and we're moving to B. So there's B. Okay, and once again we're doing the same thing here. Starting from A, and we're going to point B. Now, our next line is BD, and BD must go through points B and point D. Well, we don't know where point D is, but we do know where point B is, because point B is the point at the end there. So we know it's a 60-degree line, 60 up from the horizontal, 60 up from the horizontal, anti-clockwise up from the horizontal there. So we just draw a line at 60 degrees. So again, here's one I prepared earlier. I'm just going to move that into place now. So let's move that from the middle there, just to the intersection there. Okay, let's move, repeat move, again from the middle there. Let's move that into place there. Okay, so we've got our line at 60 degrees. Sorry, excuse me. Our next line, D to A, in this case E to A, is a horizontal line. Ooh, getting ahead of myself here. Oh, excuse me a moment, we've got somebody at the door. Okay, took an opportunity to do a little bit of tidying up as well. So, where were we? Now we're looking at D to A, and that's a horizontal line, or in this case E to A. So it goes through points E and points A, but we don't know where point E is. We don't know where point D is, but we do know where point A is in both these examples. So we can put a horizontal line in place. So I'm just going to do that very quickly. And we can see there we've got our horizontal line in place. Let's just move that A out of the way as we go. So now we just need to extend those lines so that we can close the polygon. So we'll just do that there. Is that in line? Yep, that's in line. Okay, just go to there. and same again. So we just bring that down. Is that? Yeah, that seems to be about right. Okay, so I'll just tidy up these triangles and then we'll talk through what we found out. Okay, so those triangles tidied up, and what we found out then is, in this case, point D, because that line must pass through point D and that line must pass through point D, so that corner must be point D, and likewise point E over here. Okay, for this frame. So, done that. It's a nice pretty diagram. Why do we care? Well, what we've just found out now is the size of the forces. The lengths of these lines represent the size of the forces in the members. So all we've got to do is measure them. So, it's obviously much easier with AutoCAD. So I'm just going to very quickly measure the size of these lines. There we go. So from that we can see that the force in BD is 5.8 newtons. The force in DA is 2.9 newtons, just rounding up there. The force in EB is 7.7 newtons, and the force in EA is 3.9 newtons. Okay, and that's just measuring that distance and converting that from my scale. So our next thing that we need to know is it in compression or tension? And for that we need to work out what direction these arrows are going in. So what we do is we follow the arrows around. So we know that this vector is going up because that's this vector here. So the next vector must start where our vector ends. So this diagonal line must start where our vertical line ends. And so therefore that's coming down this way. And again our horizontal line starts where this one ends, and so must be going to the right. And that's true for both these triangles. So I'll put the arrowheads on. So the arrows are on now, so we can follow that round the triangle, and again we can follow that round the triangle. So we then take these directions and we put them back around our space diagram. Okay, so let me just show you what I mean. So we've got B to D, BD here, is coming down, so towards the joint. So we're just going to copy this and we're going to bring it over here. Oops, daisy. Let's try that again, shall we? There we go. We're going to copy this and we're going to move it so it's about the joint. So our joint's that little corner there. Okay. So move from there. So it's pointing the same direction as this one. And again, we're just going to do that for DA. Okay. And then we'll see. Okay, so we've placed our arrows from our force diagram back onto our space diagram. So now we just need to zoom out. So we're zooming back out, and we're going to put that information with the arrows onto our space diagram here. Okay. So I'm just going to do that very quickly. So I've taken these arrows from here and I've placed them on our full space diagram over here. So what does that tell us? Well, at the moment it doesn't tell us a lot, but we can now look at the member as a whole. So if we have a force on the member pushing that way, well, we must have an equal and opposite reaction from the pin joint pushing in the opposite direction. Likewise, we must have an equal and opposite force at the other joint. So let me just put those arrows on. So now we can see the arrows that I've included there and there for equal and opposite reactions. So what's happening? Well, we've got a pin here and a pin here, and that means that I've got a reaction force in our beam in the opposite direction. So if we've got a reaction force in the opposite direction, means the pins are pulling out. Yeah, so the pins are pulling outwards. Yeah, so each corner is pulling out. So the reaction force from the beam is to pull inwards to hold those two pins together. So even though it looks like those arrows should be telling us that it's in compression, what those arrows are telling us is that this bottom beam, this bottom member, is in tension. Yeah, because the pins are pulling outwards. Likewise, you'd think that these arrows here would tell us that the beam was in compression, but because it's a reaction force, that means that the pins are pushing in. The joints are pushing in on the beam. So this beam is in compression. So you can see here I've put the arrows on and the reaction forces for our larger frame as well. So again, this tells us that this bar is in tension, and this tells us that this bar is in compression. So now we can fill in our tables. So we'll just do that, and then we'll move on to the next step. So there you can see we've filled in our table. So BD is 5.8 newtons in compression, and DA is 2.9 newtons and is in tension. So now we need to find out the remaining joints, or the remaining members, sorry. So for this frame, it's fairly simple because we've only got one frame left. Oh no, wait, we need to rewind a little bit. So here for this example so far, we drew each one from scratch. But some of you might be thinking, but Steve, I've already drawn A to B here. There it is, A, B, A to B. I've already drawn A to B here. Look, there it is. There it is, A to B. Why do I need to draw it again? And the answer is you don't have to. You can use your existing diagram here and build off that. You don't have to do it again. So what does that look like? Well, we would have, I'll show you in just a second. So here we've drawn our force diagram using our existing diagram that we used from our funicular diagram. So we're just building that up. Okay, so that's what that looks like. Now, over here, you can see, it's getting a little bit confusing, but let's just get rid of some of those down. Now, can you see the dimensions that we did earlier aren't in the same place? See, I just copied the triangle that we did as the triangle that we did, and that's because in drawing it again over here, I've introduced rounding errors. Yeah, because I said that line was a certain length and I rounded up. So it's possibly less confusing to do it this way, but it might be less accurate because we round up. Whereas if I'd done it from this diagram from the start, then that would be, this line here obviously would be in exactly that place there. It would be exactly at that intersection. But because I did it as a separate thing, I've already introduced rounding errors. So easier to follow, potentially less accurate. Okay, so there we go. So I'll continue to build this one up as we go, and I'm not going to do them individually. I'm going to concentrate on building on running from the funicular. But at each point you can draw it from scratch. Okay, so we'll move on to the next joint for both of these examples. So in our case here, that's going to be joint 3, and over here, well, our rules for a joint are that it must have 2 or less unknowns. So we could tackle joint 4 because there's 1, 2 things we don't know. We could tackle joint 2 because there's 1, 2 things we do know, but 1, 2 things we don't know. We can't, for example, tackle joint 5 because although we know the force in this member here, that's 1, 2, three things we don't know. Okay, so I'm going to move on to joint 2 here, because that's probably the most complicated example that we'll have to tackle. Okay, so that's our next stage. Okay, so we're just going to focus on joint 3 for a moment. So looking at joint 3, let's zoom in on joint 3. We've got C, D, and A around that joint. So we know that C to A is 5 newtons. We've already got that here, C to A. We know that D to A is, let's have a look at our table, D to A is 2.9. We've already got that. In this case it's A to D, isn't it? We're going around clockwise. A to D is 2.9. We've already got that, A to D. So the last thing we need is D to C. Well, we know point D and we know point C, so we can save ourselves actually quite a bit of time by using our existing diagram. We don't have to draw 2 of our lines again, and we know our points, so we can just do that. So all we need to do now is put our arrows in the correct place. So that's a little bit more tricky, and this is why it can get confusing. So we know, let's start with what we know. We know that C to A is an upwards 5 newtons. So let's put that arrow in the right place. Okay, so let's just move that from there to that intersection. So we know that that's going up. Yeah, and then we're following it round. Well, that arrow is going to the left about the joint, isn't it? So we're going up and we're coming along. Yeah, we're following it around, and this is just so we can find CD here. This line here. Sorry. Yes, DC. Yeah, so we always go around clockwise. Always go around clockwise. DC. So we know that C to A is going up. So we've got our up arrow there. And we know that A to D is going to the left. So we need to put a left arrow in. Okay, so let's do that. But what have I pressed? There we go. Okay. So, oh dear. Let's just drop that there. Move that from there to there. So that's going round, and then we're following this triangle round. So D to C must be coming down this way. And again, we need an arrow for that. So let's put this in the right place. There. So once again, well, the only thing we're left with is D to C, and D to C goes from there to there. So we can take that arrow and we can place it around the joint. Yeah, so let's just do that. Let's place that arrow around the joint. Okay, so every action has an equal and opposite reaction. So we must have an arrow pointing upwards and to the left there, which means that D to C is in compression. And again, we just need to take a dimension of that line to find out what it is. And what we should find, obviously, is that these are the same, 57.7, 57.74, 57.74. Okay, and that's it. We're done for that. We know everything about that. Yeah, we know all the members and whether they're in compression or tension. Okay, so that's our simple frame analysed. So I'll go away and fill in the table, and then we'll have a look at our slightly more complicated example. Okay, so we're going to zoom in on joint 2 here. That's the next thing we're going to tackle, and that's probably the most complicated example of something that we'll have to do, where we've got 1, 2, 3, 4 forces interacting. Okay, I don't think I asked you to do anything more complicated than that for the assignment. So get your head around this, and, you know, it's just repetition after that. So here we go. So I've zoomed in. There's my Bose notation around the joint, and that's what's going on. Now we know EB. Let's have a look at our table. Or BE, as I called it last time, because we were going round that corner. So we know the force in this line here. So let's label that up as well as 7.7. Okay, so let me just copy this. Yeah, it's important that we put everything that we know on the 7.7 newtons. Oops, daisy, that's not doing anything, is it? Double click. Come on, there we go. 7.7. Okay, so we know that that's 7.7 newtons as well. And we've zoomed in and we've got our own, we know which way it's going. So we could do this from scratch, in which case we draw a line at that angle here, coming up at 7 to scale, and then we draw a line at 77 coming up here, and then a line coming down at 50 from the end, and then we'd find where CF was and FE. But I'm just going to focus on adding to our diagram here. So how does that work? Well, we go from E to B, always go around clockwise, E to B. Well, E to B, we've already got there, yeah? We just need to remember this time we're going in this direction. We're going up and right, just like that arrow there. And then we have our B to C. Well, B to C we've already got. That was one of the first lines that we drew, coming down to there. Okay. So our horizontal line, C to F, well, we don't know where F is, but we know this horizontal line must pass through C. So let's quickly draw that in, and I'm just going to do that let's just make sure I'm getting the right point there. Okay, so there's our horizontal line. I'm just going to extend that out there. So that's C to F. We don't know where F is yet, but we'll find out shortly. And we've got this line here, which is F to E. Okay, well, we don't know where F is, but we do know where E is. E is this point here. So let's copy ourselves a line in the right direction, and then we can move that and place it in at point E there. Let's just zoom in, make sure we've got the right point. Okay, so we can quickly see then, if we just extend this line here, and then chop off that bit. So, and let's just trim that out as well. Let's make it look a bit neat. Okay. So we've now found point F. This is point F right here. Yeah, it's the bit where everything else meets. So let's just make that a nice lowercase f. So we found point F. And then again, we just repeat the process of measuring what we found out. So dimension, let's just pull that up, 49.2, and a dimension of 20.34. So I'll fill in the table, and I'll fill in the arrows, and I will just talk through the arrows just to make sure that we're comfortable with that. And then I'm going to stop. So I'll see you in just a moment. Okay, so here I've just deleted the other lines, so we've got a bit of clarity as to what we're looking at and what's going on. And I've highlighted the lines in this lovely purpley pinky colour. So, yeah, looking back at our space diagram, we go from B to C, we come down 5. We come down 5. Yeah, E to B, we come up E to B. And at the end of B, we come down B to C. Yeah, so we've got those two there. And we've got C to F, and draw a horizontal line through point C, and F to E, we draw a line in the same direction as that through point E, and this is the shape that we get. And so we come down and we follow the arrows around. Okay, so now we need to take these arrows on CF and FE and put them around the joint. So let's do that now then. Let's find out whether we're in compression or tension. So let's just do that very, let's just do that very quickly. Okay, so move that from there to there, and then we're going to just copy this one. Okay, and then we're going to move that from there to there. So we've got those arrows around the joint. So what happens now when we take those back to the full space diagram? Okay, right. Select, let's copy, and we're just going to copy that from the intersection there. Look at this magic. Yeah, to, isn't that the right point? There, perfect. Okay, so you can see we've now got our arrows there. So once more, we have an equal and opposite reaction at that end, and we have an equal and opposite reaction at this end. So this would be pointing back up and tells us that this arrow, this member, is surprisingly in tension. And this arrow is and we'd have a reaction force here pointing to the right, which tells us that that is in compression. So that's it, we're done. I'll just fill in those arrows and fill in the relevant bits on the table, and I'll leave the rest up to you, because all we continue on doing then is working around our frame. So all we keep doing, we just keep working around our frame. Yeah. So I'll put all the lines back on here, and you can see what it looks like with all the arrows in place. I'll fill in the table and I'll put the arrows in there, and I'll be back with you in just a second. So there we are, we can see we've got all the arrows in the right place now. So CF is in compression and FE is in tension. So we fill that in on our table, and this is how things would look over here with all arrows on. So you're just doing it this way, you've just got to be careful and work your way around for each one. Or you could leave the arrows off entirely here, I guess, and just sort of sketch, just do a quick freehand sketch and sort of follow the arrows around, which you've got the shape. That might be easier and less confusing. And then it is just kind of repetition then. So we've still got 1, 2, 3 members to find. So we could pick joint 3 or joint 4. Joint 4 would be an easy place to start. That would get us those two, but then you still have to tackle 5 or 3 at some point. But building it up over here means you have to do less work because you've already got some points already created. And it's just repetition after that. Alright, thank you very much. I hope that helps. If you've got any questions, give me a shout. Thank you. Bye.